Yeah, so I think without further ado, so we're going to start the tutorial session this morning. So first, welcome to our tutorial session. Today we are going to talk about recent advances in vision foundation models. And then I feel really blessed that there are so many people coming so in this session this morning, and I hope everyone will learn something or enjoy the session. So I will first give a high-level overview of the tutorial, and then I will also dig into one specific topic. And then other people, other speakers will follow up on other topics. Before going into the detail, I'd like to first have a kind of a brief recap of the tutorial history that we have. So actually back then in 2020, we have our first tutorial session. And at that time, we don't have VLP, we don't have vision language pre-training. And then we focus on the task-specific VQA task. And also we are in the pandemic, right? So every conference is online. And then in 2021, we have our second version. And in this version, we mainly focus on vision language pre-training. And also we focus on vision language navigation. And then come to last year, finally we have in-person conference, right? And really I enjoyed a very good in-person conference last year. And then we have a whole one-day session. Besides talking about vision language pre-training methods for the kind of traditional image text tasks, such as image captioning and VQA, we also further enrich our tutorial with topics such as how we can perform language image pre-training for image classification, object detection, and etc. So actually we have a survey paper. So yeah, so if you are interested in those recent advances, we put an archive paper last year that is on how we can quickly say the landscape of the vision language pre-training area from the basics to recent advances, and then dig into future trends. So you must be curious then what we are here today, right? So this year actually we have a brand new design of this tutorial. The reason is actually just because things are evolving really quickly, right? And then so if we look at the archive, so really the topic in the multimodal field, the papers, the number of papers, they are really growing in a weekly basis. Basically every week or even every day, we can see archive paper on this topic. And then from the language modeling perspective, right, now we have so powerful ChatGPT, GPT-4 from OpenAI. We also have Palm, Bard from Google, and also Llama from Meta, right? And then from the open source community, there are so many instruction tuned versions such as Alpaca, Vincula, etc. We also have so many large language model startups. From the computer vision perspective, everyone knows them. We also, so from the community side, we also have Dino 2 Stable Diffusion, Midjourney. We also have how we can try to have so mini GPT-4, etc. So really, what's new? So this year, so basically, we want to answer the following questions. Suppose we have an image text pair. In this case, the caption of this image is a dog is running through the grass, and such data is usually widely exists from the web, right? We can mine millions, even billions of image text files from the data, and then there's really a very rich signal inside it that we can learn from. So first, we are going to talk about the image encoder, which is the foundation, maybe foundation of the foundation. So we will first discuss how we can learn an image encoder to consume visual data. And then in terms of this, we are going to answer two questions. For one is how we can learn better image representation, possibly from the image signal only or from the image text signal. For question two, we are going to talk about how we can extend the current vision model with more flexible and promptable interface. Not only we are interested in consuming visual data, we are generally also very interested in producing visual data, right? This comes to the image generation part. So the question is how we can do image generation, and we will also cover this. And then the interesting thing is we have the large language model coming into play. LM has very strong language understanding and generation capability, especially recent in instruction tuning ones, right? So here we are going to use LM as the general purpose interface, and we are going to talk about how we can train multimodal LM and how we can train multimodal experts with those LLM. So basically, this so all these questions is the ones that we are going to answer in this tutorial. Specifically, this is the agenda. In part one, I will going to talk about visual and visual language pre-training to consume visual data. Basically, it's about how we can learn a strong image encoder. In part two, Jianwei will talk about how we can design vision interface that is interactive and promptable. In part three, Zhe Gan will talk about how we can produce visual data that is also aligned with human intent. In part four, Zhe Gan will talk about how we can make a multimodal LM that can see and chat. And finally, Lin Jie will talk about how we can train those multimodal experts with large language model to unlock new capabilities. So I think without further ado, I'm going to dig into my part, which is about visual pre-training and visual language pre-training. So as we can see, there are multiple training paradigms in this area. Supervised pre-training maybe the most classical and maybe also most the powerful ones to train an image encoder from scratch. And here comes the CLIP model, right? We can use large scale so weak supervision from the text signal to learn the image encoder. We also have contrastive learning, and actually we also have non-contrastive learning, which aims to mine the visual signals from the image. So from the image sounding. We also have mastered image modeling, which mimic the spirit of BERT, but then borrow the concept from NLP to computer vision. And here, not only in those four training paradigms, they are independent. No, they are not. They are quite so interactive with each other. And we will also briefly talk about how the community as a whole has made progress in how the different training paradigms can be integrated together. Also, as we can, this is like a disclaimer. It's there are really a vast number of literature on this topic, and then due to the time that we have, I only select the papers that I think is interesting and surely with my own bias, and then we are going to use CLIP as the anchor point to discuss the topic. So let's first have a quick recap of the supervised learning. So the supervised learning is to map an image to a discrete label, which is associated with to a visual concept. So basically, the label is a one-hot concept. During the model training process, maybe the model doesn't learn the semantics behind it. So the prompts is usually the data sets clearly or the annotation is done in a very clean manner. But the cons is that for one, the human annotation can be very expensive, and the number of labels that you can label can be limited. But then indeed, there are also many private data sets that is it's not available from public, but they indeed exist, right, from the industry lab. For example, Google's GFT 3 billion and also Meta's Instagram data sets. And in the literature, they may also call it the so-called weakly supervised pre-training. And although mostly those signals, they are weak supervision, but actually they can be very powerful in terms of learning universal embeddings. And the supervised training paradigm has also powered architectures ranging from the classical AlexNet, RansNet to the more recent vision transformer and the screen and so many other model variants. Basically, supervised learning is the test bed for all the modern vision backbones. So here, with the concept of supervised learning, here we are So we are going to quickly introduce what is CLIP. I guess most of you may already know it, but then just for background knowledge, CLIP tries to learn image representations from the web scale, noisy text supervision. So the training is very simple, right? We just use contrastive learning, and the beauty lies in large scale pre-training. So if you only have millions of image text examples, it may not be powerful. But then if you really have billions of image text files, then your zero-shot image net can go up to more than 80%, right? And then another key property is that now we can do zero-shot. We can do zero-shot image classification. We can also do zero-shot image text retrieval. For retrieval, it's easy to understand because this is basically the pre-training task you use. But then for image classification, it's mainly due to the image classification can be formatted as a retrieval task. If you consider the labels, they are not just the one hot label, but then you consider the semantics behind the label names. So the idea is really simple, and actually the idea can be dated back to a long while ago, right? So, but then in the large scale pre-training area, the pioneering work is it's a CLIP and align. And here we can see data scale really matters. So models are frequently measured. Models are frequently trained with billions of image text files. And also, so basically, if you want to scale a model, there could be 3 dimensions, right? The data scale, model scale, and the bench size scale. So because it's a contrastive learning, so usually we will need a very large bench size to do a good job. So this is one quote that I quoted from the Flip paper, which is one paper from CVPR this year that I feel really agree with it. So in the sense, language is a stronger form of supervision than classical closed-set labels. And the language provides rich information for supervision. And then scaling is a very important factor, both in terms of model scaling and also data scaling. And especially, I think this sentence is very good. It's CLIP is an outstanding example of simple algorithm that scale well. So I think really, when we have a simple algorithm, but then if it has a very good scaling property, it can really unlock many of the potentials that previous model have never been seen before. So this is CLIP basically, right? And then, so I think since the birth of CLIP, tons of follow-up works has been emerged in in archive, in CVPR, in all the conferences. So here I'm going to talk about some of the recent follow-ups that I think is interesting. So I think for one is data scaling, right? You have the image, you have the text, but then how can you further scale it up? The second point is model design, how we can design better models out of the original CLIP. I'm also going to cover briefly about the objective function. Contrastive pre-training is indeed powerful, right? But then what's the other objectives people have been using? Or can we get some inspiration from them? So for data scaling, I think in this year's CVPR, and then so I think there's a paper, it's called the reproducible scaling law for CLIP training. So basically using the open source large scale around 2 billion data sets, they can pre-train the open CLIP model across various scales. And then recently, another interesting paper is the data camp. So we know scale matters, especially the data scale, right? But then how we can further scale it up? Are we just scaling it up using noisy and noisier data? And I think in this paper, they propose a very nice idea is in search of the next generation image text data sets. So I think the idea is instead of fixing the data set and designing different algorithms, which is basically what we do every day. And in this paper, the authors propose to fix the CLIP training methods. Basically, this is the training algorithm. It's fixed. You just provide me the data set, and then the data set will just go through fixed training methods, and then you are going to play the game of selecting the data rather than playing the game of selecting the model. So I think so by the end, the authors come up with a large scale data set that has a high performance. For example, in zero-shot ImageNet. So in terms of model design, from the image side, I think one recent interesting paper is the FLIP paper. So I think in terms of training, it still use the original CLIP loss, and even the MIM loss is not used because later on they will show the MIM loss is basically not useful to enhance the CLIP model. But then the trick is, here we the authors propose to randomly mask out image patches within with a high masking ratio, and then only encoding the visible patches. So the idea is very simple and it's more like a trick, right? So given the image as your input, you are not going to encode the full image as your input, but rather you just randomly mask out the images, like what you do in MAE or in MIM, but then do the original CLIP training. And after doing this, the authors have shown that it doesn't hurt performance, and actually it can improve your training efficiency by a lot. So from the language side, one paper that I think is interesting is how we can enrich the language that you have been using external knowledge. And here, when we say external knowledge, it basically means the Wikipedia definition of entities or the so-called knowledge. So that, so for example, so in this figure, there's a motivating example. Maybe if you are not familiar with Japanese food, right? Maybe you don't know what is sashimi, but then if you provide a definition of sashimi, maybe you don't know the concept of sashimi, but still you can kind of know what does sashimi mean from its definition. So that if you enhance your language side, enhance your language input with such data, it can help you learn a better CLIP model. And actually in the small scale setting, the authors have shown that enriching alt text with entity description can enhance the performance. We can also say work to improve the interpretability, right? And here is one paper called Cell. So instead of mapping images and the text into a relatively low dimensional but dense embedding space, here we can also try to map the image and the text into a very high dimensional space. But in this high dimensional space, it is very sparse. So each dimension in the sparse embedding is a subword in a very large dictionary, basically covering your whole vocabulary. But then the weight associated to each dimension means how important corresponds to the weight associated with the token. So as you can see, given the original caption, so if you follow this idea from the information retrieval literature, basically you are going to learn more interpretable embedding by grounding your embedding directly to tokens, but in a sparse manner. We also have image bind. This is a very recent work, right? The idea is quite simple. It's basically now you have more than, for other modalities, it may not be easy for you to scale up, but then for image text, it's really easy for you to scale up. Then how about you use the fixed pre-trained CLIP model, right? So basically, the idea is you are going to link all the other modalities to the CLIP embedding space. So yeah, so actually, yeah, this basically means you don't need, so if you have a pre-trained CLIP embedding, you can always try to upgrade the CLIP model by aligning this CLIP embedding space to some other modalities. And then if you can do this, you can try to unlock some new capabilities that you may not be able to do before, right? And in the paper, they also show they can do, usually we do text to image generation, right? But here they can do audio to image generation. But really it's, you get an audio as input, but then due to your audio and the text, they are in the same space, then you just map your audio into an embedding, so without changing anything. And then I'm going to talk about objective function. One paper is fine-grained supervision. Besides the contrastive loss we are going to use, people have been developing how we can provide more fine-grained supervision. And in this paper, they have been shown if we trying to learn the word patch alignment during your training process, then you can enhance the performance and get a better CLIP model. For example, in the visualization, they show instead of just compressing image into one feature vector, text into another feature vector, and do the dot product. Here, we also propose to learn the word patch alignment so that the model kind of capture the fine-grained information. So another interesting idea is COCA, right? How about we add in a generative branch? So I think this is always what we do if you see the traditional vision language so literature, right? But then I think the key concept in this paper is that they are not just interested in VQA and image captioning, but really they want to learn the image encoder from scratch. So treating COCA as image encoder learning methods. So instead, so here they use mixed image text and image label data for pre-training, but then they add another generative branch for enhanced performance. And due to the use of the generative branch, they can also encode new capabilities such as captioning and VQA. Yeah, they similar to many other vision language model, but then the model is purely trained from scratch. You must be curious about how about we learn the image, whether we can learn image encoder from scratch just using the image captioning loss, right? And indeed it's possible. So how about using the captioning loss again? So I think the whole wave of using image text supervision, right, to learn image encoder. So I think the beginning, so I mean, if we really want to date back to the literature, it can be so dated back further, right? But recently, I think it's due to the introduction of Vortex, right? So in the Vortex paper, they also propose to use the COCO, although it's very small scale, it's using COCO data, but then they show using the image captioning loss, indeed can learn image encoder from scratch. But then in CLIP, the authors show contrastive pre-training is much more effective. And then in the CVPR paper, the authors also show the learned image encoder was actually, the same message, not competitive compared with CLIP. But then in the recent paper, also by Google Brain, CAP and CAPA, the authors actually argue that image captioners can be scalable vision learners too. And the captioning exhibits the same or even better scaling behavior. So I think this is also one interesting message they deliver in the paper is just using the simple image captioning objective. You can learn very good image encoder. And especially when you use such image encoder for downstream tasks that so deals with multimodal fusion. Yeah. So another interesting topic that I like to briefly discuss is can CLIP be combined with other learning approaches? And this also provides us with a nice way to connect with other learning approaches. So we will first briefly talk about supervised learning. So not only we have supervision from text, we also have supervision from the label, right? And I think for supervised learning, the problem is you can learn discriminative visual representation, but the con is that you have only limited visual concepts. But on the other hand, for CLIP kind of model, you have broad semantic coverage, but your representation may not be discriminative enough. And in this UniCell paper, the authors propose a principled way to use both image label and image text data together for learning a strong image encoder. And the scale-up version is the Florence model. Besides that, we can also say there are some other methods trying to do that, right? Because your image encoder can learn a very discriminative representation. So in the LIT paper, the authors basically propose you first pre-train the image encoder using image text data. And in this scale, it can be GFT 3 billion. But then based on this frozen image encoder, then you can make the model open vocabulary. by just learning an additional text power. So basically, the idea is just to teach a text model to read out a good representation from a pre-trained image encoder to new tasks. And then by doing this, they also show much improved performance. And recently, we also have the MOFAT paper. So trying to learn image representation from noisy entity annotated images. So here the authors proposed the I2E data, and I think this is the largest data set of its kind in terms of the number of entities they have been using. So as you can see, the authors have collected 1 billion images with 2 million entities. So the message is that if you want to do supervised pre-training, then you'd better you have a large number of labels that you want to predict from. So going beyond the ImageNet 1K and possibly ImageNet 22K, right? So by using such data sets, the authors show that on the image-to-image retrieval benchmark, which can have wider industry use, the performance can be improved a lot compared with the original CLIP model. And this is some of the example of the I2E dataset. So in terms of learning, it's also very simple. For supervised learning, right? It's basically you treat the entities as labels. And the only difference is now you have 2 million labels rather than, for example, 20K labels. So though this is a very classical method, it's very effective for image-to-image retrieval tasks, actually. And then for CLIP, we can treat entity name as free-form text, as we usually do for all the CLIP model training. And then we can also enrich them with entity description. So this is some idea very similar to PayLight, but now in a much larger scale. And then they also combine supervised pre-training and CLIP for multitasking, and they show strong performance to learn image backbone with performance so even better than the Dino V2 paper. So I think the combination of CLIP and the supervised pre-training is positive, right? Then how about we combine CLIP with some of, so for example, image-only contrastive learning methods, right? So I think we can have first have a very high-level overview of so what is contrastive learning of visual representation, if you are not familiar. So just in case. So I think CVPR is kind of a very classical paper, right, to do such a job. So basically, all the papers they are following the same paradigm. It's basically you have you given one image, right? Then you are going to generate two different views of the same image, and then you have a base encoder followed by a projection head, which is trained to maximize the agreement using the contrastive loss. And then the projection head will be thrown away for downstream tasks. And then the methods can also, due to the use of contrastive loss, you can always try to connect with mutual information maximization literature. But then, so as you can see, this is basically all the same framework for all the so image-only contrastive learning, right? You have one input image, then get a different augmentation. Then you are trying to learn a contrastive model from it. But then the caveat is you will need a very large bench size, for example, for CVPR training, or you will need a very large memory bank, for example, for the MOCA training, right? And indeed, in the literature, people gradually find that we can relieve the dependency on negative examples. For example, the use of negatives can be replaced by asymmetric architectures, dimension decorrelation, and also can be replaced by clustering. So basically, instead of using negatives as the regularization, people have been trying to use different methods to provide such regularization so that the model will not just learn a trivial solution, right? And then the left is one example from the CIM7 paper, and on the right is the Dino. And the Dino is basically using the self-distillation idea. So, but as you can see, no matter how the different training algorithms, so it's a design, you will always have one input X And this one input X will become two inputs, which is X1 and X2 here. And this X1 and X2, they will go into an encoder. And this encoder can be the same, or can be different, or can be a momentum contrast, or can be an exponential moving average, right? And usually you will have a stop gradient operator on one side, or either you do not have it, but then you need to add other regularization to make it work. Okay, so this is the very quick overview of the contrastive learning, right? But then how we can combine together with the CLIP kind of training. So I think one paper is the D-CLIP paper, right? The high-level message is supervision can exist everywhere. So they propose to enhance the CLIP training with self-supervised learning on each modality. For example, in the image side, they use in the SIM-SAM loss as well. And then we also have the CLIP paper, right? And the idea is even simpler. It's simply combine SIM-CLR and the CLIP for model training. And by doing this, in an academic setup, they show they can have better zero-shot transfer and linear block performance. We can also try to make CLIP non-contrastive, right? As the name suggests, the contrastive language image pre-training. But then can we similar like how the non-contrastive learning methods have been used for image-only self-supervised learning? So here, can we explore the idea of making the CLIP model non-contrastive? And actually the answer is yes, right? So without using negatives, we can ensure non-trivial solution while some regularization term. And this is some regularization term from this paper. So as you can see in the CLIP model, right, you have the positive path, and then you also have the negative path to make the model learn general representation. But in the unclip setup, the model will only using a positive path to learn such such model. But then there's also some bad news is that only using, so different from the image-only literature, only using unclip or the non-contrastive clip is not enough for strong performance, and it needs to be used together with the original clip. So basically, the proposed X clip in their paper is a combination of clip and unclip. It's like you are using an additional unclip as the regularization term for you to learn a better performance. Okay, and this is good, right? Since the message is also positive. So then I'm going to briefly discuss master image modeling. So I think BATE is one important work in this field, right? So the high-level idea is, can we perform BERT-like pre-training of image transformer, just like what we do in BERT literature? So as you can see from the figure, before the pre-training, we need to learn an image tokenizer, which can be the WQVE or WQGAN, right? And then this we are trying to tokenize your input image into a set of discrete visual tokens. And these discrete visual tokens will be used as your training target. To learn the image encoder. So the similar approaches have also been used for image generation, such as DAE and PATI. And the idea is you will randomly masking the image batches, and then you will pre-train the model to predict, as I just said, pre-train the model to predict those masked visual tokens. Actually, it can also be understood as knowledge distillation, right? As you can see, there's a image tokenizer, and this image tokenizer is kind of the teacher. And you also have the beta encoder, and this beta encoder is kind of the student. But it's only now the student is doing a much harder job, because your student can only see partial image instead of the whole image as your input. Many people say MIM is more like a fine-tuning method because it can show strong fine-tuning performance, right? Compared with so starting from scratch. But it kind of seems not like a representation learning methods due to the model itself cannot provide a single global image representation, right? So it can be good for fine-tuning. And then later work, the famous one, right? The MAE, they show, oh, you don't need to use discrete tokenizer. Why not using pixel directly? And actually, it can indeed work, right? You just randomly mask out the images, and then your encoder will apply on those visible patches, and then it works, right? And then besides using pixels, why not using other features? And in the mask field paper, they also have shown in actually many other so features can also be used as target as well. And one special one they find is so work is the so-called very traditional hop feature. So as I just mentioned, there could be some potential problem with the naive MIM. The first one is the scaling probably may not be that clear compared with CLIP. So MIM is very scalable in terms of the model size. You can train the model from small size goes to 1 billion or even larger. But then from the data, data scaling perspective, usually those models are pre-trained on the ImageNet 21K data set, right? They did not go even further, or when they go even further, they did not see some meaningful improvement. So I think that indeed there are some recent work trying to study whether MIM is also scalable in terms of the data size. But I think the conclusion is still not conclusive yet. And so at least those models do not go to billion scale so images. So I think MIM is good for model fine-tuning, but since not learn a global image representation, although there are some remedies such as the Abbott paper is basically or roughly, what did I do? Yeah, that's like a surprise. So for example, Abbott is a combination of the Dino and also the bait paper and the bait idea, right? And then this idea also be adapted to the Dino V2 paper. So indeed, in the paper they show the bait itself cannot learn a global image representation, right? As you can see, the red box, the linear probe performance is actually quite low, right? But then, if you can see from the left, if you trying to enforce to push your information inside the sales token, then the model can learn global so information. Okay, so before talking about the CLIP and the combination of CLIP and the masked image modeling, actually we talked about the combination of image-only contrastive learning and masked image modeling. So then can CLIP and MIM can combine it together? So I think there could be two kinds of combination, right? For one is a shallow combination, right? Shallow combination is a kind of you use these two models interactively, or actually it turns out the image feature from CLIP can be very useful or can be a very good target for MIM training. Partially is due to, because now the target is CLIP feature, right? So the CLIP feature can capture the semantics that is missing in the MIM training. This is one approach. It's the MVP paper, ECCV last year. They for the model that you are going to learn, right? So they will directly regress to the CLIP feature. And then in the V2 paper, instead of directly trying to regress the CLIP feature, the authors using another idea, but basically it's similar. It's you are trying to compress your CLIP information into your visual tokenizer. And then after you get this new set of visual tokenizer, you can do the bait training as usual. So basically it's another way of using CLIP feature into your model training. But then you must be curious, then the real, so really the whole training pipeline is really very long, right? Yeah, and so I think this approach is further kind of popularized by the EVA series of work. In the EVA paper, they first use CLIP to train MIM, and then in their later work, they use CLIP as the initialization to train the CLIP model. And then finally they say, hey, this is an alternative learning, right? So it's like you have your CLIP model, which can be used to train your MIM model using CLIP as the target, right? And then on the other hand, after you train the MIM, you can use the MIM as the initialization to train your CLIP model. And then, as you can see, due to MIM is very good at model fine-tuning, right? So the fine-tuning can be used for hardcore task if you care about fine-tuning performance, right? But then the CLIP model can be used for zero-shot task you may be interested in. And then in this paper, they showed these two can have a kind of very good synergy so between them, so which is nice. As you can see, this is kind of a shallow interaction between CLIP and MIM. So I think in the community, they also work trying to investigate, can we have a deeper integration? So I believe some of them come into papers, and some of them due to its negative results, right? So it's never into a paper. But indeed, since currently it's more like a negative answer. So in this paper, masked autoencoding does not help natural language supervision at the scale. They also show at a small scale, since MIM is useful to have CLIP, but if you do it in a larger scale, this doesn't help. This is also a CVPR paper this year. And actually in the flip paper, in the very beginning I mentioned, right? They also show this is negative. So by the end, they didn't use MIM. So by the end, the authors didn't use MIM, right? And then reframe their story to say I can improve CLIP, so training efficiency by randomly masking out the image patches, right? But then if you dig into the paper, in their ablation study, they indeed show in this training paradigm, seems naively combine them together will not lead to a stronger backbone. So I think I'm going to conclude. But before conclude, indeed, the CLIP and MIM, they are not positive, but BERT and MIM, they are positive, right? So this is, you can try to combine BERT and the BERT together. This is intuitive, right? Because they are both just to do masking, right? And I think I have checked it all, the points here. So besides backbone, we also have many other backbone, right? We didn't discuss, but then really, we don't have that much time, but really we have a lot of backbones other than VIT, such as the convex and the interimage. And here come to a high-level summary. So in this brief part of my tutorial, I centered around the CLIP, and we discussed how we can train a strong image backbone as foundation. And actually, we only focus on image level pre-training. We didn't touch region level pre-training or pixel level pre-training, such as CLIP, SAM, XDecode, etc. Because actually, they typically will use a pre-trained image encoder as a first hand, right? So, so the image encoder pre-training is like the foundation of the foundation. If you consider SAM, XDecoder, CLIP as foundation, right? And it's just some observation. We can see some high-level principle. Scaling, contrasting, masking is something like the general design principle behind all these methods. And for future challenges, really, I don't know what to say, but then, yeah, I'm just trying to list some. How to further scale up, how to further scale it up, especially in terms of model sets, right? Because we know vision foundation models typically are much smaller than the language counterparts. Maybe also new model training paradigm. But then if you want to have a new model training paradigm to be popular, it's better to be simple. But then it also means it's so very difficult to design such an algorithm. Also, how we can perform unified image region pixel level pre-training, which I will leave to my next speaker. It's also very challenging to say how we can extend the current vision model with more flexible and comfortable interface, which my next speaker will also talk about it. Finally, how we can train vision foundation models with more innovative data, right? If we check about the GPT-4 paper, right? If you provide a scanned PDF summary of one paper, the GPT-4 model can even just summarize the paper for you, right? So how this kind of capabilities can emerge? But then if we just use natural images, this can never happen, right? But then how can we? I don't know. But then how can we train vision backbone with more innovative data? This is something that I'm interested in. But then till now, although all the papers I have been talking about is all about this small point, is how we can consume visual data. And then the other speakers will talk about the rest. And yeah, so I think I will stop here and thank you.